When we look at metals and metallic bonding, it's quite a bit different from ionic or covalent, where we say that this atom and this atom are doing a specific thing to interact with one another. Metals normally have low effective nuclear charges. Some have a lot of shielding, which means fairly low ionization energies. The valence electrons farthest from the nucleus are easily lost or easily pulled away from those atoms. The metallic bond itself is the attraction between the remaining cation or metallic nucleus and core electrons to those few valence electrons, which are not tied to a specific atom. The best word to use for that is delocalized. We describe them as free moving, but that doesn't mean that they're always flowing around. It just means that they're not stuck to a specific atom at a given time. We still have an attraction that can be described by Coulomb's law between the nucleus and those electrons, and different radii impact that in different ways. Here, it's asking why things are able to be malleable. So the malleability, the ductility, and the conductivity of metals is based upon the fact that we can rearrange those atoms while still surrounding them with some electrons. The planes or the molecules themselves are likely to stay bonded in some directions, but as I flatten it out or draw it into a wire, I can change where some of those are relative to one another. When we make an alloy, a mixture of atoms, sometimes we keep the same properties, sometimes we kind of emphasize some of the properties, while other properties become a little bit less emphasized or are weaker. So this is saying some alloys are just as malleable while others are not. The alloy that's going to be more rigid would be an interstitial alloy. If we're thinking about the ability to be malleable based upon particles and atoms kind of sliding past one another into that new position, when we have a substitutional alloy, the one atom and the other atom are very similar in size and act very similarly. So they can slide past one another, probably with very similar amount of energy. When we have an interstitial alloy, we're putting little bumps or little atoms between them. So if we're trying to slide past, we would meet some resistance, and those things would get in the way. That difference is intentionally exploited when trying to make certain things harder. We substitute in a smaller atom, creating an interstitial rather than substitutional alloy, making it a little bit harder and more difficult to change its shape. For the next one, we're also asked about alloys here. We're thinking about radius to know, is it substitutional or interstitial? So gold and platinum are right behind me here. They are next to one another on the periodic table. That means they have the same number of energy levels. They have a similar number of valence electrons. They have a similar effective nuclear charge. So they're probably going to be fairly similar in size and shielding in radius. Because they're the same size, that means that they're much more likely to be substitutional rather than interstitial. You could even be given specific radius values in a question, maybe in a data table, and looking at how close they are to one another rather than just looking for general patterns based upon trends.